the work presented here on the simulation of rogue wave statistics in supercontinuum generation optical fibers is a collaboration of 3 universities: Rudolf Römer at Warwick University, Akihiro Maruta at Osaka University, and myself, Mark Eberhard, at Aston University. I will first give you a short introduction to the field of optical communications, then explain the modeling equations that we use for the simulation, go into the details of how the parallel method is being implemented, look at the scalability results we achieved on some supercomputers, plus then come to the physics and to the results of the research that we've got so far, rogue wave statistics, and finish with some conclusions on there. First, to the introduction. Optical communication systems have been around for quite some time, and the first and earliest optical communication systems were typically alarm signals, so you had sort of fire beacons, smoke signals, but they wouldn't really carry a lot of information on there. The first really useful optical networks was something which we could now call free space optics, and that first network was suggested by Claude Chappé in 1792, and effectively the first optical network in Europe was completed in 1830. What you can see is an image here of an optical telegraph, and what you would see is the constellation of these arms on the optical telegraphs. They would be changed to different constellations to transmit some information on there. Interestingly enough, at that time they already thought about things like error correction, and they thought about how to optimize these constellations. And in that sense it is similar to what you have in modern communication systems in there, because there also you use different constellations, although these are now optical signals and optical fibers and not sort of free space visual impacts on there. And of course the components that would regenerate and repeat the signal are electronic or optical components, and at this time it would have been human beings which from a distance away would watch this tower, would watch the constellations, write down the message, and then operate their own arms on their tower to forward the message around. And of course the bit rate at that time, which was about 1 bit per second, has slightly improved. So when we're talking about modern optical communication systems, we're typically talking not about a free space system like this, but rather we're talking about a system that is based on transmission in optical fiber. The idea is fairly simple. You have a glass, typically a glass core, and you have a cladding around the glass core, and if you launch light at a shallow enough angle into the fiber, then it propagates by total internal reflection along the fiber. But the biggest problem initially in the 1960s was that there was a huge loss of about 1000 dB per kilometer for light to travel down on the fiber on there. Investigations then turned out that the main reason for this high loss was impurities in the glass, and so as manufacturing processes improved to reduce the impurities in the glass, in the 1970s that loss went down to about 20 dB per kilometer, and modern fibers now with even further optimized losses get down to about 0.2 dB per kilometer. It's important to note that these losses are at about 1.5 micrometers wavelength of the light being transmitted, which is in the infrared range, and that is the typical range that is also now used in communication systems to transmit a signal on there. The 0.2 dB is now not down to impurities, but it is more down to intrinsic fiber losses because of the interaction of light with the molecules in the fiber in there. So with low losses in the infrared range, we have a medium where we can send a signal with very low losses over fairly large distances on there. However, we still have to look at what different modes such a fiber supports in there. And if you look at the structure, it's basically a cylindrical structure. We have a core and a cladding, which is shown here. And the ratio of the inner core, which is diameter of the inner core, is A, and the radius of the cladding, which is B on there, plus the different indices for the refractive index, N1 and N2, they determine the mode structure of what modes can propagate in a fiber. And obviously N1, the inner refractive index, is slightly larger than the one in the cladding, so we're going from an optically denser medium to an optically less dense medium, and that's why we're getting total internal reflections. It turns out on analysis that fibers do support two types of modes, which are denoted as HEMN and EHMN. Now, for m equals 0, these modes are equivalent to the classical TE and TM modes that are found in other systems. However, for m larger than 0, these are hybrid modes. That means all 6 components of the electrical and magnetic field are different from 0, and so it is a more complex type of wave structure on there. When the first fibers were built, these were multi-mode fibers, which means that there were different modes that could propagate, and because these different modes do have different group velocities, even if you launch light at a single wavelength, you would still get a dispersion at the end of the fiber, simply because it is launched in the form of different modes which travel at different speeds, and so your signal gets distorted. So in the 1980s, the single mode fibers were invented, where basically this whole setup, the range of the ratio of A to B and the ratio of N1 and N2 were optimized in a way that the fiber only transmit a single mode. There's only a single mode can actually propagate. And this mode is an HE11 mode. And most modern single mode fibers today are based on this principle. It's worth noting that this step index profile, as it is called, is one possibility. It is also possible to use diffusion to change the refractive index, and in that case, instead of a step profile, you do get a continuous change of the profile in there. And there are also, for specialty fibers, where you have sort of multiple cores in there, or where you have air holes, air gaps in there. But these are all sort of used for special purposes. For the normal purpose of optical communication systems, we basically have a single mode fiber, and that is still the standard that is being used on there. The propagation of light in an optical fiber is of course based and modeled using the Maxwell equations, but directly integrating the Maxwell equations would be too much of a computational effort, and so we use an approximation. And there are several things which help us to derive a sort of more efficient numerical model. One is that a fiber is cylindrical, and that the axis along the fiber, the z-axis, is of course hundreds of kilometers in a communication system, while it is only a few micrometers in the xy direction perpendicular to the fiber direction on there. So we can use that. We then also put in the interactions that we know between the fiber and the light traveling through the fiber, and if you work all of this out, you end up with an equation which is of the type of a nonlinear Schrödinger equation, and this equation is the one which is most commonly used to describe light propagation in optical fibers. So if you look at this equation in more detail, we've got different terms in there. First of all, we've got the derivative of Z. U, our field, is the envelope of the electrical field that's traveling along the fiber. We then have, first of all, a term alpha over 2 times U, that is the loss term. So this basically describes the attenuation of the signal as it travels along the fiber. We then have a second derivative of U times beta 2. This is the dispersion, so this is the change of group velocity in the fiber. And you notice we don't have a beta 1 term, because 1 over beta 1 would be the group velocity. And it's important to note here that we always look at simulating the optical signal in what we call a moving frame. So basically, we do look at a short piece of fiber, we look at the signal that is in the short piece of fiber, and this is our time axis t, and then we watch the signal that's in this short piece of fiber as it travels along the fiber. So we change our z position from where we look at the fiber, and we move along the fiber at the main group velocity. That basically means if I have, for example, 20 or 30 picoseconds worth of data on the fiber, and I'm looking at this as my signal, then because I'm traveling along the fiber at the same speed as the signal, I do see, for example, these pulses that are on the fiber, I do see them, they appear to be standing still, but of course, because I'm traveling down the fiber along with the signal, I can still see how these change due to imperfections in the fiber, due to dispersion, dispersion slope, and nonlinearity. And this is a very useful way because it allows us to monitor a signal has been launched into the fiber as it propagates along the fiber and as it changes. Now, the first effect after beta 1, after the group velocity, which we transformed out, is the dispersion. The dispersion is the change of group velocity with wavelength. And the shorter the pulses in the signal, the wider their spectrum, and so the more dispersion they do experience, because the difference in group velocities between different spectral components in the signal is larger on there. We then have the next term, the beta 3 term. This term is the change of the dispersion with wavelength and its dispersion slope. we will see that this term will become later in our analysis when we're talking about rogue waves, because this is going to play a very crucial role for the formation of rogue waves, and also in our analysis as to when do we get rogue waves and when we don't. This completes the linear part of the equation, and we will later on see that this is the part which we solve in the frequency domain, because then the time derivatives simply become multiplications with powers of omega. So the second time derivative becomes an omega squared, the third becomes an omega to the power of 3, and so that part is very easily solvable as an equation in the frequency domain. On the other side of the equation sign, we've got the nonlinear part, and here we've got the nonlinear parameter gamma, and the nonlinear parameter gamma is now multiplied by the instant power of the field times the field. This is our self-phase modulation term, which is basically the power of the field. U squared is the optical power of the field, times U, which is the envelope of the field. We then have further terms. We have a shock term, which is relevant if you have very short pulses on there. We will neglect this in our simulations. We're not going to use that term. And we also have a delayed Raman response, and again that is a term that we do neglect and that we do not use in our simulations for these purposes. So what we include is the dispersion slope, and the self-phase modulation. When we look at an optical communication system, we typically have hundreds of kilometers, and in that case the loss term alpha that we've got here plays an important role because it attenuates our signal. But because we're looking in this example at supercontinuum generation, we only have short distances up to 1.5 kilometers, and if we're looking at a loss of 0.2 dB, or for the wavelength range that we have of 1 dB per kilometer, then the attenuation caused by alpha is very small, and for that reason we don't need to take alpha into account. So for the simulation of supercontinuum generation, we will look at the beta 2 term, we will look at the beta 3 term, and we will look at the self-phase modulation term, and neglect all other terms. One interesting question is whether there are analytic solutions for this equation, and it turns out that this equation does support what is called a soliton solution, and this analytical soliton solution needs we need to delete the beta 3 term, and we need to delete the shock term and the delayed Raman response, and also the attenuation. So if you only keep the dispersion term and the nonlinearity, which are by far the most dominant terms in the equations, all the other terms do add small additional contributions. They're not perturbations, but they're fairly small compared to the beta 2 and to gamma, to the nonlinearity. So if you take these two dominant terms only into account, then we do get an analytic solution, which originally was found by using the inverse scattering method, but of course the easier way to test this is by just putting the solution into the equation and see if it fits. And we're getting out that we're getting a second hyperbolicus equation times an exponential term, and that describes a pulse which stably propagates through the nonlinear Schrödinger equation. This has been shown experimentally, so this is all proven and well established on there. The important thing to note on this one is the relation that we have between the width of the pulse and the peak power, because this is a formula. This will appear later on when we also look at modulation instability. This fraction, the square root of a fraction of the beta 2 term, the dispersion, divided by the nonlinearity times the peak power, plays a crucial role, as we will see later on there. The important point here is that the larger the peak power is, the smaller T0 or the pulse width goes. So if we have a large peak power, we get very narrow pulses. If you have a small peak power, we get rather wider and larger pulses out of it. Now, that's the basic equation on how we model the system. However, how do we numerically implement that? If you want to numerically implement this, we have to first look at the classical way to solve the nonlinear Schrödinger equation. It turns out that the most efficient way is to look at the first part of the equation, the linear part, and to solve the linear part of the equations in the frequency domain. As I've mentioned before, the derivatives in time, the third derivative of time and the second derivative of time, these ones convert into an omega square and omega 3 term if you convert the equation into the frequency domain. So this becomes very easy. You can just write down the analytic solution, and it's very easy to apply that solution to our field. On the other hand, the nonlinear terms are not that easily transformable in the frequency domain, because we've got the u square, we've got the power in there, and these terms are more difficult. So that part is on the other hand, easily solvable in the time domain because it's all instant in the time domain. We also have to think about how we parallelize that. And it's easy to parallelize the linear part in the frequency domain because this is piecewise working on different frequencies. It's also easy to parallelize the part of the nonlinear part because in the time domain that is localized. So we can chop this up into blocks, into chunks, and work on them on different cores, on different machines. And the only communication that is needed is a bit of halo data overlap if you wanted to include the delayed Raman response, because you would need to calculate a time derivative, so we would need one data value to the left, one data value to the right when we evaluate the power on that. But that is something which isn't too difficult to, it's a small amount. The big problem is, because we're doing what's called an operator splitting method, we need to convert the signal constantly from the time domain to the frequency domain. So we start off in the time domain, we apply the nonlinear part, we then go through a forward fast Fourier transform to transform the signal into the frequency domain. Then we apply the solution, the analytic solution part for the linear part in the frequency domain, and then finally we use a backwards transformation to get back to the time domain. And that one we do go around in circles. And every time we go around a circle, we move our field forward by a small fraction delta z in our equation in there. As I already said, the linear part and the nonlinear part are easy to distribute because they work piecewise on the elements of the array U, which stores the envelope of the field. However, the fast Fourier transform and the forward and backward fast Fourier transform, these are non-local operations. They require a huge amount of change. Basically, every second element in a Fourier transform needs to be remapped and needs to be shuffled around between the different steps of the Fourier transform. So the forward and backward Fourier transforms are the bottlenecks which are very difficult to parallelize. To overcome that problem, we split the whole system into individual blocks, and we try to work on these blocks individually on there. And this is shown on the next slide. So we now have our signal U, and we have a block I, we have a block I plus 1, we have a block I plus 2, we have a block I plus 3, and so on. The problem with that approach is of course, that the signal in block I is not self-contained. The end of block I is the beginning of block I plus 1. Now, if you would only use block I, do a Fourier transform, apply our linear part, then we would get problems from wraparound effects, because the Fourier transform assumes that we've got a periodic signal, which we don't in this case. What we can do now is that we overlap these blocks, and this is part of the overlap. So what we do is we take data, say, from, if you're looking at block I plus 2, then we're taking data from block I plus 1, and these data are copied down at the start of a larger block which also contains I plus 2. We also take data from block I plus 3, and that data is copied at the end of block I plus 2. So we're extending each block to a larger size, and we do copy data from the previous and the next block. We can work out that we need half a block or a quarter of the larger block size as halo data, and then the wraparound effects will of course still happen. They will still pollute the data, but the polluted data will all be in these extra added halo data at the end of the block, and so the actual core of the block will not be affected by wraparound effects. And so by copying the start and the end of the previous or the next block into our current block, we can get to a signal which we can do a Fourier translation only on a block, and then later on unwrap this again. We also want to have several blocks per MPI rank. The reason for that is that we can then adjust the amount of these so-called halo data at the end, because as is shown here, block I plus 3 is being held on MPI rank J, while block I plus 4 and subsequent block are being held on MPI rank J plus 1. That means that the start of block I plus 4 needs to come from block I plus 3. So this is halo data that needs to be copied from rank J to rank J plus 1. On the other hand, the data at the end of block I plus 3 is data that comes from rank J plus 1 and needs to be copied to rank J. By being able to use different numbers of blocks per MPI rank, we can adjust the ratio of the amount of halo data that needs to be exchanged between the different cores and the total amount of data we work on. This becomes important if our interconnect has a high latency, or if we want to increase the parallelism of the problem. So we have a performance adjustment parameter which we can play with, and that way make sure that we're not entirely dominated by communication in the system. And we will look at the optimum value of the number of blocks per core when we do the performance and scalability analysis on this. And with this trick we can now parallelize the FFT, and with having parallelized the FFT we have the other operations already in a way that they can be executed in parallel, and we have now everything we need to successfully run our simulation on a large cluster on multiple cores. The next part of this presentation will now focus on the scalability results that we have observed on 2 supercomputers and on one loose cluster of workstations, the cow, and we will compare the performance and we will analyze how the code performs on these ones. The first machine that we look at is Hector. Hector is a large supercomputer at the University of Edinburgh. It's funded by EPSRC and it has a total of 90,000 cores, but the largest job class you can run is 65,000 cores. And you can see when you look at the scalability results that it seems to be scaling very nicely, very linearly on there. However, if you just look at the speed up over the number of cores that we've got here, then you can't see much detail, and so it is better to look at the relative performance, where you divide the speed up by the number of cores, and that of course turns this straight line into a horizontal line, and it reveals more details. But before we do this, let me explain a bit more about what's actually being plotted here. We have 2 possible types of simulations that we're running on here. We could parallelize what we call MPI only, and that means that every core is its own MPI rank. So even if we have a CPU that has multiple cores, we still associate one MPI rank with each core. So that is a completely MPI only based implementation. However, we also have the possibility to parallelize using MPI with a combination of OpenMP. In this case, we have one MPI rank per node, but within a node, all the cores within a node are parallelized using OpenMP. These solid and dotted lines are then used with the 4 different colors that we've got for our 4 different test cases that we're running on here. You can't see it at the moment on here. If you look very carefully, you can see the dotted here, but the performance is very similar, but the differences will become apparent when we look at the relative performance, because then these details are better to see. Now, the 4 test cases that we ran here in red and green is the case where we actually switch the overlap and discard off on the FFT, which means in this case we're running independent simulations. We have independent blocks, we have an independent wraparound on each block on there, and that means we have no halo data communication, and the jobs are basically running independently of each other. So in that case we can see the performance when we're just CPU limited, and we need that as a comparison, both in terms of results, because that is the typical way how you would run a simulation. If you wouldn't distribute it on a large cluster, you'd run many independent simulations, you would average over these simulations, and you would then compare the result from that to the result of having one very large time window on there. The blue and the magenta curves, these are the ones where we switch our overlap discard method on, and here we now have the halo data exchange for every forward FFT, and of course we do expect in terms of runtime performance that we will see a difference between the two, and we will be able to separate the purely computational part in the scalability and the part which is due to the overhead of communication. So let's now divide that by the number of cores, and then we should see the performance. I should also say the parameter beta3 tilde should not affect the computational complexity of the problem, so we would expect that the red and the green should have about the same performance as the blue and the magenta, because it's just a numerical parameter which doesn't change anything on the complexity on there. So we can see, if we see differences between the red and the green curve, or difference between the blue and the magenta curve, then we know that these are statistical deviations from simulation run to simulation run, and these are not consistent or deterministic delays in the code in there. So let's divide the speed up by the number of cores to get the relative performance. And now we can see, interestingly enough, that we do have for a start a very large drop at small numbers of cores. So we do see going from 1 core to 8 cores, we see a dramatic drop. On Hector, there are 8 cores per NUMA region on the processor, and there are 32 cores per node. So basically we're seeing a drop off to about 70% of the performance when we go from a single core to using all cores within the NUMA region. We also see now that the dotted lines, which represent the OpenMP parallelization, does perform slightly worse than the MPI only, and we will see that feature in all the other runs. So for some reason the OpenMP implementation does have a less performance than an MPI only implementation. The reason might be that because in OpenMP we parallelize the blocks, but we do not explicitly assign data structures to threads, that if the OpenMP implementation moves threads between cores, that this includes extra memory copy, extra overhead, and that slows the performance down. And then we also see if you go to very large core counts, so if you're using on the order between 16,000 and 65,000 cores, we do also see a drop in performance here. Now this is most likely caused now by the interconnect when we go over the whole machine. Remember, the Hector has 90,000 cores and 65,000 cores uses 2/3 of the machine on this job size, and apparently at that point when we communicate all across the machine we do see some drop off in performance in there. But the major drop off is right at the start, is going from 1 to 8 cores. And if you look closer at this problem and wonder where this is coming from and analyze this, then you very quickly realize that this must have something to do with the actual structure of the cores and the structure of the CPU being used on Hector on that, because this happens not between nodes, this happens within a node, even within a single NUMA region. And the explanation for that is quite simple. If you look at the CPU architecture that's being used on the nodes on Hector, these are AMD Bulldozer CPUs. These consist, as you can see, of 4 module blocks per NUMA region. Each module block does have 2 cores, called integer cluster 1 and integer cluster 2. However, it has only a single FPU. So effectively, in this AMD processor, 2 cores share a single FPU, and this is the bottleneck that we're seeing why the performance is dropping off. We can test that by allocating only every second core. So we can say we allocate 4 threads to 8 cores, and basically always leaving the second core idle. So we allocate 1 thread to integer cluster 1 on module block 1, 1 thread to integer cluster 1 on module 2, and so on. And then we do have a dedicated FPU for each of the individual cores on there. If you do that, then we would expect that this drop off in performance from going from 1 to 8 cores disappears. And not surprisingly, that is the case. This is again the speed up now, and we call this low density because we only use every second core. That line looks straight, but even when we divide this by the number of cores, we still see that we're now achieving a scalability of 95%. We've only ran these up to 1024 cores because we're interested in this case on the performance up to 8 cores, where we did see the big drop off initially on there. But it's also nice to see that now if you're going up to 8 cores, we do have about the same performance for the case with overlap discard on and with overlap discard off. Now 8 cores means we're going across 2 NUMA regions, and 16 cores means that we're using a complete node. So we see a bit of a drop off for communication within a node, and then of course past the 16 cores we're going onto network, so we're taking a small hit here. But once we're on the network, on the interconnect on Hector, we'll see that the performance is pretty much constant for the exchange of the Halo data up to 1024 cores. So that scales very well, and this is what you would expect because we basically have a ring topology where we exchange data with the left and the right neighbor on there. One can also draw the carp flat metric, which shows the serial portion of the code. This is now using all cores on Hector, and what we can see here is initially we see a huge serial part in the code. Now I'm saying code, but this doesn't necessarily have to be in the code. This can equally be in the hardware. And as the case with Hector, if you use all cores, because you've got two cores fighting for one FPU, this drop-off in performance actually is created by serialization in the hardware and not in the software. You can see that if we now switch to use only every second core, so that we now have a dedicated FPU for each core, then this serial fraction from about 30% that we're seeing here suddenly goes down to almost zero. Again, we can see that the OpenMP performance is worse than the MPI performance on there, and that is something which is subject to further investigations to find out why that is the case. There is no principal reason why the OpenMP implementation would be slower than the MPI only implementation on there. But what it shows very clearly is that if you want to get maximum performance on Hector, you cannot use all the cores, because you're then limited by serialization in the hardware as two cores fight for one FPU on there. Next, after Hector, we're looking at the scalability result for the supercomputer called Minerva. This supercomputer is installed at the University of Warwick and is operated by the Center for Scientific Computing. If you look at the speed up here, we're having a core count of 5,760 on the machine. If you're looking at this core count, we again see a very nice linear scale up for the code, and if you look at the relative performance, we can now see that this machine has an interconnect which is slightly worse than the interconnect that we find on Hector. You can clearly see there is the same drop off that we've witnessed before when we're looking at OpenMP. So OpenMP fares significantly worse for reasons that we need to determine yet. But we also see that if you go for larger and larger number of cores, that we now do see a more pronounced drop in performance than we've seen on Hector. This could either be the interconnect, which is slower on Minerva than it is on Hector, or it could be desynchronization of processes on the individual compute nodes. It's difficult to tell the difference. The drops that we see in performance for a certain number of core counts are statistically not significant, because we can see if you rerun jobs and we did run the same number of cores for different block sizes, we do see that these do change. So there seems to be a lot of statistical fluctuations. Again, this would point to that the latency and that the throughput of the interconnect on Minerva is far less deterministic and sort of far more random than the throughput that we've seen on the interconnect on Hector. We can show this also by just looking at the user time. So far we've seen the real time, the wall clock time, that was measured while the job was running. However, we can also look at the CPU time that's reported by the machine and by the processors, and then we see that the scalability looks very fine. Now the difference between this and the previous slide is simply delays and waiting. So again, it could be, we can't differentiate at this point here whether this is desynchronization of threads on the different compute nodes, which of course gets worse the more cores you use, because that means you have more threads that can possibly desynchronize, and the performance is determined by the slowest core, because that's what all the other cores have to wait for before they've reached the next MPI barrier and can continue with the computation on there. So the code seems to be fine, but clearly there's a bit of an issue on the interconnect. The carb flat matrix, nevertheless, for Minerva also looks fine. It's very close to zero, and that gives us an example again of a machine which is a good supercomputer machine with 5,760 cores. We're getting a good performance, good linear scale up on there. We also looked, for the fun of it, onto something which is called a cluster of workstations. This is a task farm device machine, and we're only going to 32 cores. This has two dual core processors in each node. So we do see a nice performance going up to 4 cores, because that's when we're inside one node. But the moment we leave that, we're getting an Ethernet gigabit Ethernet interconnect, and we basically see moving from 4 to 8 cores. This is when we move from the node, move onto the gigabit Ethernet network. We basically gain no performance, because anything we gain by using twice as many cores, we just lose in the latency and by the time it takes to send messages around between the two machines on there. It's also clear to see in the relative performance part, we see we're basically dropping to about 50% of the performance that we had before. while the purely compute bound parts, the red and the green curve, which don't exchange any hello data, that of course stays nicely, because here the CPUs just continue with their computation and there is no communication overhead involved in it on that. The carb flat matrix equally shows that we've got some peaks here. We show large serial parts, and of course a large parallel code is not suitable for a task farm, because a task farm is not designed for parallel computation. A task farm is designed for many individual jobs that have no communication at all. And so this is a test really to see what's happening if you run such a large parallel code on a machine that is unsuitable for it, and you get the result that you get very poor performance out of doing so. I'm now going to look at the difference it makes in the number of blocks. I've mentioned this when I've described the numerical algorithm, that the number of blocks tells us how much halo data we have per computational effort on that. If we have too few blocks per core, then we're dominated by communication, because we have a lot of communication to do but very little computational work. On the other hand, if we go to a large number of blocks, then we do use a lot of memory on each node, and we're probably then limited by the memory bandwidth that we've got on this node. But we expect somewhere in between a trade-off where we get most of the data are still in the cache of the CPU, so they're very fast accessible on the processor, but at the same time we're having the benefit of having less halo data for the amount, and somewhere there is an optimum. And you can clearly see this if you use all cores on Hector, but this maximum is somewhere between using 8 to 16 blocks in our computation per core. We can again look at this and say what's going to happen if we reduce the number of cores that we use on Hector. And then we would expect, because we now only use every second core, we have one core idle, so that means we're doubling the amount of cache memory available, and so we expect this to shift basically by a factor of 2 upwards. And that is what we see when we try this. So we can see, well, we had the optimum between 8 and 16 on using all the cores. We now have the maximum shifted up to 16 to 32 in case that we only use every second core. But otherwise we can still see that we're around that area with 16 to 32 is where we find the optimum performance, and that will be the number of blocks that will be used for simulations. Continuing on Minerva, we do see that we have a much flatter curve. So Minerva, in that case, the CPUs do a much better job in terms of keeping with larger data sets. So the flexibility to choose any core number from something like 8 blocks up to 64 and more cores works fine, and we don't really see any large performance penalty of doing this on Minerva. The cow, of course, this is where we expect things to get worse. We don't have a lot of cache memory on there, so we're dropping off here on the memory, and of course we're getting a huge penalty from only using 1 block if we run on the cow, because this is the very, very long latency and low quality of service Ethernet, gigabit Ethernet interconnect. So that's not a surprising result, and it shows us that if you want to run on such a task farm, you need a large number of cores, and you do still get very large statistical fluctuations on the performance from the machine on there. We can now look in more detail at what the performance data tell us. We have 4 blocks, 4 or more blocks in our actual computation. One is the forward FFT, one is the backward FFT. We've got the linear part, the nonlinear part, and we also have parts which do calculate the spectrum of the signal and parts which calculate the power of the signal. The forward FFT, which we're looking here now, is a good example, because in the case of the red and green curves, we have no communication overhead. These are independent, so this is purely computationally bound. And here we see an absolutely flat curve up to 65,000 cores on Hector, but we see the initial drop-off up to 16 cores, which is again caused by the concurrency between the 2 cores to 1 FPU. On the blue and magenta curve, we do now have the exchange of constant halo data, which is clearly visible. That reduces the performance compared to the case where we have no halo data exchange, but because it's a constant amount of halo data exchange and it's a ring topology between left and right neighbors, we do see that this, once we've taken the initial hit to go out onto the network, that stays pretty much constant. And we only see here for very large core counts, we do see some slight deviation where we believe this is the interconnect which is slowing things a bit down. If we now only use every second core to see what's going to happen to the initial drop off, where we expect of course this to be much better, then we can see this now is fine. We get a pretty much 95% performance on the non-communication part, and we now clearly see that up to 8 cores, which means half a node, we getting a good performance agreement. Then when we go to 16 cores, this now means we're using all the 32 cores on a node, because we're only using every second core. So there we're taking some hit. So most of the hit actually goes down to 85% is taken before we go out onto the interconnect of the network. This is before we start. This is really communication within the node. And then we're taking another hit when we're going out onto the network. 32 cores, this means we're now using 2 nodes on Hector. So now we have all the communication within a node for the Halo data exchange, plus we have the communication overhead to go to the next node. And because we expect this to be sort of the whole penalty of we expect things to be flat from here. And this is what you can see. So from then on, the performance stays at 80% and goes flat over there to large core counters. Again, note that the OpenMP implementation is significantly slower than the MPR only implementation, and that is also nicely visible on here. Doing the same on Minerva shows that we're getting an absolutely perfect plain 100% performance on the red and green part on the jobs which have no Halo data exchange. So computationally that's working fine. However, if you look on the one where we have Halo data exchange, we do see significant fluctuations from different core counts, and this is if you would rerun the simulation, you would expect again to see this fluctuating here. Also we see a drop in here, which is statistical on there. So clearly the interconnect that we have on Minerva for the Halo, despite this being a ring topology, the interconnect on Minerva is no match for the interconnect that is available on Hector. Also again note the drop off for the OpenMP performance that we've got on here. And last but not least, looking at the cow performance wise, we do see that of course the communication is the big killer. Up to 4 cores, we're within 1 node, we're still having a decent performance. The moment we go out onto the network, we're dropping suddenly to less than 20% performance. Not surprising, while the jobs which have no communication stay at full power. So clearly the communication is important, and you do need a fast and a very deterministic interconnect with deterministic latency and deterministic delay times in there to get a good performance out of the code on that. The second I want to look at is now to look at using different numbers of blocks. We can again see whether we're at the optimum point or not. And we can see now for the forward FFT on Hector, we do get again a maximum around and about 16 blocks per core, so we're pretty close with our 8 cores. That looks fine, but we do see then a performance drop off if you go to a larger number of blocks per core. This again is now memory bandwidth. The FFT is non-local, so once it has to reload data from memory and cannot use data from the cache, it will suffer in performance in there. Doing the same calculation for the low density, we can see a much better performance. You can see an almost perfect scaling for 32, where we're hiding the whole latency in there, and even with Halo data exchange, we're getting the same performance as we get before when we were looking at the job which has no Halo data exchange on there. Interesting enough, also the OpenMP for a large number of blocks per core is now catching up and actually overtaking, as well as for a very low number on there. So that's some observation which probably needs some further investigation in there. On Minerva, we're seeing a very flat performance from 8 cores upwards. We're seeing the hit, of course, for a large number of blocks, because then the communication part is too strong. But we do see the very flat performance as we go along from about 8 cores on there. And we also see the pretty constant performance for the part which does not exchange any Halo data. Again, OpenMP, you can use it, but the performance for 8 blocks is below the one with MPR only, but it does catch up, and eventually for a larger number of blocks, the OpenMP and the MPR only seem to be on par. Going to the cow, we see the picture that we've seen before. We have a very low performance if you have a small number of blocks, basically less than 10%, only 5% performance on here. Not surprising. This is now purely the dramatic effect of the interconnect. And you can see between 95% performance without communication to 5% performance with communication. And only when we go to something in excess of 64 blocks per core, we can actually compensate for the long latency and for the non-deterministic timing on the gigabit Ethernet interconnect. So if we have a machine with a very slow interconnect, we do need to use a large number of blocks per core. But if you have a machine with a very good interconnect, we can actually parallelize much better. We need less blocks per core, and so we can get a much faster answer, because the interconnect allows us to have less work per core and thus a faster performance. The second sub-block to look at is the power statistics. And the power statistics is interesting because it is computationally not a lot of work. All it does is communication. It only calculates the absolute value of the envelope U, which is the power of the field, but then it has to do a tree reduction over all the cores to calculate what is the average power and the maximum power for the whole field in there. And we do see, for the case of the on-off, the overload discard being disabled, we do see an almost constant performance on there after we had the initial drop-off again, which we blame on the CPUs. But then we do suddenly see, to say, from 4,000 cores upwards, we do see a drop-off in performance going to 65,000. So clearly this cross-communication, this tree communication over the whole cluster, over all the cores, does start to suffer quite badly as you get to use larger parts of the machine in there. The reason why this is so flat is because on the case of the overlap discard method being switched off, being disabled, we have put an MPI barrier in front of the code that does the tree reduction on the power, so we can actually see the performance of the tree reduction. That is not the case in the blue and magenta curve, because otherwise it would show the same performance on there. In this case, we do not have an MPI barrier just in front of the power reduction, so we do see the desynchronization of the threads of the job they were doing before, because now in the reduction model we have to wait for the slowest core, and we can see that there's quite a difference in performance if we have to wait for the actual cores to all reach the same point in their computation and then start to exchange data. Interestingly enough, OpenMP performs much worse on all of these, but performs similar for the case with overlap discard on and off. So what this appears to suggest is that there is some internal extra synchronization barriers in OpenMP which are actually throttling the performance, which are not there if we're using MPI only. Doing the same calculation using only every second core on Hector now shows us that we get nice flat scalability up to 1024 cores, and we do see a divergence if you do use the exchange, if you don't have a synchronization barrier. So basically, the more cores we have, the larger is the chance that one of those cores will be slower than all the other cores on there. So we're getting more statistical fluctuations, and of course the slowest core, when that's ready to send the data, that's when we can only start to reduce the data over all the cores, and so we do see a performance drop. If you know, in the red-green case, that waiting for the slowest core is done in the MPI barrier before we actually invoke the reduction operation, while we don't have the MPI barrier in the blue and magenta case, and so we do see desynchronization of threads, of computational threads on there. Going to Minerva, we do see that leaving a core, and on Minerva we have 12 cores per node. We have 6 cores per CPU and 2 CPUs, so we have 12 cores per node on there. However, we do see, the moment we go out onto network, you do see quite a significant performance drop in this operation, again confirming the observation that we made before, that the interconnect on Minerva is significantly less constant, is less deterministic, which is also seen on the large fluctuations that we do see here. Despite having an MPI barrier before and having no desynchronization of threads from the computation, we still see large fluctuations, and these fluctuations clearly are latencies in the interconnect, in undeterministic latencies in the interconnect. So here the difference between the interconnect on Hector and the interconnect on Minerva shows up very, very clearly, because this part of the code is determined basically by the performance of the interconnect on there. Last but not least, looking at the power statistics on the cluster of workstations, We do expect this to fare fairly badly, and this is also what we see. We see a performance drop sometimes down to 5, because of course here we've got the very slow gigabit Ethernet interconnect, and we don't expect this interconnect to have any sensible performance at all. We can also analyze this again for different numbers of blocks per core, and we see again the optimum is somewhere around 16 to 32 blocks on hectare if you use all the cores. And we now see nicely for both of them that they increase from 1 core up to a larger number of cores. And we see a very perfectly type of scaling on here with the MPI barrier in front for the red and green curve. And we see slightly less pronounced for if you don't have the barrier in front of the reduction operation in there. Doing that for the low density on hectare shows that we now need up to 32 to 64 cores to get an optimum performance out of it. And so if we're running at 8 cores, we're only getting about 60 to 70% performance. And it doesn't show up in the overall runtime for the simulation because these reduction operations do not happen very often, and so they're not computationally a very large part of the computation in there. But however, if you have a core which requires very frequent reduction operations, then of course this would show up, and one would need to use a larger number of blocks to get to an optimum performance on there. On Minerva, the picture looks similar. We're moving up all the way, and it doesn't seem that we're already hitting saturation. So for reduction operations, as you would expect on a slower interconnect, we would need well in excess of the 64 blocks we need per core to mask the latency introduced by the interconnect for that. Then finally, looking at the cow, we do see incredibly large statistical fluctuations. Again, not a surprise. The gigabit Ethernet doesn't have any really proper timing that we can use. It is very unreliable in terms of being deterministic as to how quick things happen, when things happen, and so we don't expect there to get a reliable constant performance out of it if you go to a larger number of cores or blocks. It's simply the latency can be so large if you get a packet loss or packet collision on the gigabit Ethernet switches on there that you're just being set back and your whole process is slowed down. Remember, the slowest one determines the performance of the whole program, because we have to wait for the last processor to finish, and before that's finished, before that has completed its communication, we can't continue with the simulation. And so that is on the gigabit Ethernet, we do have a very significant penalty on there, and such a machine is not suitable for running these types of massively parallel simulations. Now that we have looked at the scalability of the code, it is interesting to look what this code is actually doing and calculating. And that brings us to the topic of rogue waves. And before we look into the statistics for rogue waves, we need to understand what is actually happening in our system. And the first point to look at is modulation instability and the method that actually generating the supercontinuum. So what we're doing is we're shining a single laser light with a single wavelength of 1064 nanometers into our fiber. What happens is, if you put this solution, a constant CW light, into the nonlinear Schrödinger equation, you can find out by linear stability analysis that this is unstable in the anomalous dispersion range. It would be stable in the normal dispersion range. But as you can see, our beta 2 is negative. It is minus 2.6. So we are in the anomalous region, and so we do expect the constant CW solution to be unstable. We can work out what's actually happening. So if we have at our zero frequency, which corresponds to our lambda of 1064 nanometers in this case, if you pump in light at a certain power at only this wavelength, so basically a laser diode shining into the fiber, then we will generate energy next to it. So we're pumping in at that frequency, but we do get energy transferred to frequencies nearby. The frequency that is transferred depends on the power. In our system we have a power of 10 watt, and that means we're transferring energy to something about 4.5 terahertz plus minus the frequency that we've put in. Where does this result come from? Well, this result comes from a linear stability analysis of the nonlinear Schrödinger equation with a constant CW input, so a constant power value going in as the initial condition. And that allows us, the stability allows us to derive what we call the gain spectrum. The formula for that is given here, which then depends on beta 2, it depends on the power, and it depends on the nonlinearity. Remember, this term that's showing up here is very similar to what we've seen for the soliton, and that of course shines up here, because what's happening is we have a constant power shining into the fiber, and because of the modulation instability, because we're pumping energy into nearby frequencies at a positive and negative frequency, this constant light that's shining into the fiber actually breaks down into a train of pulses. And we can also work out roughly what the spacing of these pulses is that we expect. And it turns out that for 10 watt of power in this incident power, we do expect a pulse spacing of 226 femtoseconds. So we're expecting roughly a bit more than 4 pulses per picosecond to come out of our system on that. The formula to calculate this, the time spacing, is again given on the top here. Now with that knowledge, we can then look at the actual propagation constant, and this is where these values of beta 2 and beta 3 come into play. We in optics develop the k of omega. Normally for a dispersion relation it is written as omega as a function of k, but in optics we develop the actual propagation constant, which is called beta and not k. Develop this as a function of omega, do a Taylor expansion around our zero frequency, omega 0, which in our case corresponds to 1770 terahertz, which is the corresponding frequency for 1064 nanometers, which is the wavelength of our laser light that we're shining in. So we are developing this, and if you have no beta 3 term, we're getting the brown curve for the propagation constant, so we're just getting a simple quadratic equation, and we don't get any positive beta values, we only get negative beta values out from there. That's because of course our beta 2 is negative one here. We now have a beta 3 of plus 4.4 10 to the minus 3 picosecond to the third per kilometer, and because we want to switch this on and off, we introduce another dimensionless prefactor, beta 3 tilde, and this factor we will vary now from 0 to 1, and we will look for the different cases later on when we look at the actual results of the simulation to see what effect does beta have. So we're switching this on from 0 to 1, and beta 3 tilde 1 means that we're using a beta 3 of 4.4 10 to the power minus 3. Beta 1 will not show up in our simulation because this is only there if we haven't included the group velocity. Because we're looking at a system with a moving frame, of course beta 1 is 0, and we're also not including a constant phase. So the only thing that is included in our simulation, because we're in a moving frame, are the terms for beta 2 and the term for beta 3. Importantly now, if we switch beta 3 on, so if beta 3 tilde is not equal 0, we're getting more zero crossings for our beta function on there. These zero crossings depend on the value of beta 3 tilde, and I've got here the different wavelengths that shows when it's crossing. You will find later on that these are also drawn as dotted lines in the spectrum from the simulations, so you can easily recognize where these 0 points are. These 0 points basically mean that we've got the same phase velocity at these wavelengths for a particular beta 3 tilde as we have for the main carrier frequency at 1064 nanometers, which is here. You can also look, if you want to see the dispersion relation in the normal way that it's shown, as a function of omega of k over k, and keep in mind this is a delta omega, this is omega of k minus omega 0, minus our carrier frequency of the light. Then you see sort of we have this parabola on the left hand side for beta 3 tilde equals 0, and then we have our third order term, we get these extra zero crossings here going off, and we obviously then get frequencies in there. Now with that analysis done, we can understand the principal features, because we will see that in modulation instability, first of all we have our gain spectrum, so we're pumping from our zero frequency, we're pumping energy nearby according to the gain spectrum, but because of the phase matching condition on where the extra zero crossing induced by a finite beta 3 term, we will also have a phase matching here, and it will turn out we're also pumping energy into these wavelengths, and we will see a peak at the corresponding frequency or wavelengths to come up later on in the simulation. And that brings us straight away to rogue wave statistics. So what are rogue waves? Rogue waves are unusually high waves. And the reason we're interested in is because these waves significantly exceed the largest waves that we normally have in a system, and if they become too large, then of course they not only can affect the signal in terms of optical communications, and that means induce extra errors, but in the worst case that can also mean that we're damaging the system. Interesting enough, the nonlinear Schrödinger equation also describes water waves in deep water. So these rogue waves also are equivalent, what we see in optics, equivalent to unusually large waves on the oceans, and these are responsible for actually sinking ships. Now, why we're interested in statistics, these events don't happen very often, they are rare events. However, if one of these rogue waves has the possibility to damage the equipment of a communication system, or has the possibility to sink a large container ship, then we want to know what the probability is. Because it's a rare event, we do need a huge set of samples so we can actually resolve the statistics at this very, very low probability point, so we can then make a reasonable estimate as to how likely is it to happen and what is sort of the worst case that we would need to prepare for. Let's look at how the simulation actually works. We start off at a distance of 0 meters before we start traveling down the fiber. We do have a constant power of 10 watt. You can see that scale starts at 0 here. We have slightly offset, we are at 10 watt. We have a constant power. This is in the time domain. This looks at something like approximately 6 millimeters length of fiber, and we're looking at the signal that we do have in these 6 millimeters of fiber in here. We're also doing a statistic on the distribution of power levels in the signal. Now in this case we have a delta function to start with. This is 0 power, this is 200 watt, and we are at 10 watt, because obviously we have a constant amplitude of 10 watt, so we have a delta function in here. We also plot the spectrum in here, and we do see that spectrum again is sort of a delta function around our black dotted line, which is our 1064 nanometers, the frequency or the wavelength of the laser diode that we're shining in. And we're showing here the extra 0 crossings of the beta 3 term, and the red dotted line means that is for a beta 3 tilde of 1, and the blue one means it is for a beta 3 tilde of 0.45. Now I'm showing in the power spectrum and in the probability density function, I'm showing 3 different values of beta 3. 0, no beta 3. This is sort of the classical case, where we have analytic soliton solutions and we don't expect to see much of an issue. We also have beta 3 equals 1, this is sort of the extremest case, and we have a case in middle beta 3 tilde equals 0.45. In the time diagram, we're only showing the value for beta 3 0.45, because otherwise it's hard to see what's happening on there. When we start the simulation and we move on to a distance of 41 meters, we'll see first of all the gain spectrum that we've seen from the modulation instability. So we see these side peaks coming up on the side of it, and we also see the next order coming up, which is sort of, because this is a cascaded process. First of all, we get from the instability, we get the gain spectrum pumping up a peak next to the frequency that we've put in. We then see that this peak, of course, at a lower power pumps the next one, but because that power is lower, the gain spectrum is more narrow, as we've seen from the previous slide. And so in the end we're expecting to see something like a triangular shape. Please also note that this is a log scale and this is also a log scale. You can also see that this is starting to widen, and if you look very carefully you can see sort of slight wiggles on the line in the time domain. If you move now another 40 meters, we're going to 80 meters, we see the situation has changed quite dramatically. There's a lot happening in these 40 meters. That spectrum here has broadened. We see now almost a triangular shape for our spectrum here. We see this spectrum looks similar for the case of beta 3 tilde equals 0 and beta 3 tilde equals 0.45, while the spectrum for beta 3 tilde equals 1 has already an extra peak and broadens. We see at the red dotted line where we have the phase matching condition where the red peak goes up, and we see here the blue dotted line where we have for beta 3 equals 0.45 the extra, we see how the peak's coming up here. We also see that in the PDF we're now getting a distribution of different power levels, and our powers now go from 0 up to roughly 120 watt. Further, when we look down in the time domain, we can see that we have roughly 1, 2, 3, 4 pulses per picosecond, which is in accordance with what we calculated before, that we expect a pulse spacing of roughly 226 femtoseconds per pulse. Of course, that is only an estimate. We do not get a regular pulse train, we do get an irregular pulse train, but on average we get roughly about four pulses now per picosecond, and that is what we expect as the ballpark figure. Now we move further on from 80 meters, we go now to 250 meters. At that point we can see that the spectrum for beta 3 equals 0 is now a nice symmetric triangular shaped spectrum on there. We've seen for 0.45 that we've got a more stronger pronounced peak here, and we see for 1.0 a vastly broadened spectrum. We can also see in the time domain that it looks similar. We don't have this regular pulse train, we have only isolated peaks, but otherwise it looks very similar. And in fact, if you look at the PDF, we also see that the case for 0, beta 3 and 0.45 look similar, while the case for beta 3 equals 1 already shows significantly larger power levels. At least go up to an average of 300 watt, and they go up to 350 larger powers on there. If we integrate that system further down to 800, about over 800 meters, we can now see how the spectrum has broadened further, except for the spectrum for the case of beta 3 being 0. That spectrum has maintained its shape. However, the 1.0 spectrum, this got much broader, and the 0.45 spectrum, the blue one, also broadened on there. You can also see now that, and this is the important thing on the rogue wave statistics here, is while for the case of beta 3 being 0, we're just getting a straight line, which means we're getting an exponentially decreasing probability of finding larger amplitudes, we see a massive enhanced probability for getting large amplitudes in the case of beta 3 equals 1. You have sort of a completely different fall off. You can also see that we're here 50 dBs down from the peak of the distribution, so these cases are 100,000 times less likely to appear. And this is the reason why we need such big and massive simulations with large data sets, so that we can actually resolve the shape of this curve. And you can see from the broadness of this one here, this really is statistics. So if you would go for a bigger machine, and if you would use more cores on an even bigger machine, you could resolve that statistics even better, and we could get down to lower probabilities in here. And that is the crucial point why we do need this massively parallel algorithm. The time, we see smaller, more narrow pulses here emerging on there, but otherwise it does look unchanged. We do not yet see an emergence of rogue waves in here, but we do see from the PDF that we do have fairly large peak powers in this case, which can go up to 500 watt, which would be the top of the scale on here. In the case of 1.0, we're already exceeding a power of 800 watt. But if you continue the simulation for larger distances and move on to 1374 meters, then we can see that now the blue spectrum, the 0.45 spectrum, has broadened significantly beyond that. It now almost matches the PDF for the case of 1.0, and we also have captured here a case where you have one of these rogue waves of about 500 watt peak power. You can see these are incredibly narrow, and these peaks do move through the spectrum. This is another important feature. If we have beta 3 equals 0, we have our modulation instability, and we have these waves appearing and disappearing, but they are stationary. They don't move to earlier or later times. They travel basically at the main group velocity. However, these peaks, as we've seen in a moment, they do travel at a different speed. They basically travel across the spectrum here. And one of the mechanisms how they gain energy is that they move on and they take energy from the pulses they do cross over. We can see this more clearly when we look at a 3-dimensional or 2-dimensional plot, where we're now plotting the distance on one axis, our time on the other axis, and our power on the z-axis. We see at the start we have our initial power of 10 watt. We then see the onset of modulation instability, where we see this regular pulse train forming, and for the case of beta 3 equals 0, nothing specific happens. We do see this modulation instability existing, and we do see waves. The same can be seen more easily also in the 2-dimensional plot, where we see that these ones, the pulses broaden. Dark means higher peak power, grey means lower power, so we start from a unique 10 watt. We then see these sharpening up into a pulse train, and these pulses are stationary. They move a bit around, they bounce off each other depending on the phase. These are basically solitons forming and interacting with each other, but otherwise this is sort of almost vertical here. So we can see these don't really move in time or change in time. If we increase beta 3, this suddenly changes. So if you move beta 3 and can increase it to 0.35, so we have a third order term, we suddenly see that something new happens here. We see that we get a collision as before, but instead of these bouncing off and then continuing straight on, we see now an emerging pulse, and this one's moving sideways. Compared to all the other ones, which move like straight lines up, this one's now moving sideways. And we also see that there is another one emitted in the other side. We will see that as we increase beta 3, the one going to the left hand side gets more pronounced and stronger, while the one to the right hand side is more and more suppressed. If you invert the sign of beta 3, this is the other way around, so this depends on the sign of beta 3. You can also see this very nicely in the three-dimensional plot. If you look here, you can see sort of the peak emerging. These peaks are much larger than the peaks around. You see a whole train of peaks going along here, and at the start these peaks oscillate, but they can stabilize, become large peaks which move through. And you can also see where they've got the energy from, because there's a void here. There's this very flat area in here, which also can be seen. This white area means that all the energy that has been in here has been combined into this stronger pulse. This is now moving across, collecting more energy as it goes along. If you look at a case where we look at a larger distance already, we're sort of at 1,000 meters to 1,400 meters, where many of these pulses have formed, we can actually see a collision of two of them. We have one pulse moving across this way, and we have one pulse moving across this way. And like soliton pulses, you can see these lines here, they can cross each other, they can move through each other, collide like solitons, and after the collision remain unchanged and escape as they were before. So these pulses can cross, so they have a sort of soliton-like behavior on there. If we then increase beta 3 to the maximum value of 1.0, we can see now the whole process is much quicker. From the modulation instability, we straight away see pulses forming. We see these pulses take the energy out, so there's sort of only a flat type of landscape left. There are no normal oscillations from the modulation instability left in there. Instead, we get pulses forming. These draw up all the energy, and once they've soaked up all the energy, there's not much left. You can see it clearly here. As they gain energy, they accelerate and move faster to the left. It's not a completely linear process. You can see there's sort of very much variation around it on there. But you can see what's left here is just sort of very, very little low power noise and light. But most of all, we now have only pulses that are moving through the system, and the whole system breaks down. So that is the way how rogue waves start to exist and come into existence. What we next need to study, of course, is to look into the mechanism. What exactly causes these pulses to emerge, and how do these pulses gain energy as we move along? That will be the subject of further investigations on that. But we have shown that we can do very good statistics on this. We can at least now capture how likely is it for these rogue waves to start to appear, and what other statistics, what is their likelihood to get, for example, a rogue wave of 800 watt, of 600 watt, of 700 watt. We have good statistics on that because of this massively parallel approach, where we can use a very, very large data set. These simulations, I didn't mention this, show only a small part of the simulation window, since this is labeled from 7 to 12.5 picoseconds. But of course, we have many, many thousands of picoseconds, even nanoseconds in the whole simulation. This is just a very small fraction of it, just to visualize what is going on in the simulation. And because we have this huge number of pulses which we are calculating the probability distribution function over, that's why we're getting these statistics down to events which are 100,000 times less likely than other events, where we can still have reliable statistics and say how often do they occur, what is their probability on there. And that brings me to the end of the presentation and to the conclusions. We have a new simulation code, massively parallel, which works, is validated and scales. The results that we're producing are in accordance with our numerical estimates, with our analytical estimates. That looks all fine. The code does the right thing. We can also see, when we look at the different supercomputers we've used, that Hector has a fantastic interconnect, but the choice of the AMD CPUs, where two cores share an FPU, is not ideal, and clearly that is a bit hard to understand, taking that this machine has such a fantastic interconnect and it's such a large machine on there. On the other hand, Minerva at the CSC has fantastic CPUs in there. They don't show any of the problems that the AMD CPUs do show on Hector. However, the interconnect is significantly less deterministic, and for larger core counts we do see a decrease in performance there, which appears to be latency, undeterministic latency in the interconnect. So what would be great will of course be a machine which has the interconnect from Hector but has the CPUs that are in Minerva, and that would really be a very helpful and good choice. We also have shown that we can simulate rogue waves and we can obtain high quality statistics even for the rarest events in the simulation, and we have seen that the dispersion slope does play an important and crucial role. We do only get a simple exponential decay of the probability function if we have no third order term. We do get a vastly enhanced probability for large rogue waves, large power levels, if we do have a third order term included on that. We still need to do a lot of extra work. There is work that we need to understand what's limiting the OpenMP performance. As that there is no theoretical reason why OpenMP should perform worse than a pure MPI implementation. In fact, it is the same binary that's being used for the tests. The pure MPI case simply uses OpenMP threads equals 1, but there is sort of no difference in the source code, no difference in the binary that's running on that. And that needs a bit of that's a bit to look into to understand. There are also further possibilities to optimize the code. At the moment, communication and computation are not overlapped, which means if there is communication, there is no computation going on, and if some computation hasn't finished, when communication is needed, the code has to wait. Well, that can be overlapped to some extent, and that can also increase the performance because both things can happen at the same time, and this is one of the optimizations that we hope to put in very soon. MPI topologies may help with the performance. We have seen on Hector that for very large core counts that the performance starts to drop off. If we would tell the system that we're using a ring topology or a tree topology for the reduction tree topology, for the Halo data exchange ring topology, then this may lead to a more optimum distribution of the MPI rings among the cores, and it could help for very large core counts on Hector. We haven't tried this, this is a possibility. And last but not least, what we're going to start very soon is also that the code structure is already prepared and suitable to implement it on GPUs, and that is the next step, that we will use CUDA and trying to implement fat node structure and then have many CUDA cards working together, communicating via MPI, and see how that scales, how well that works. But based on the performance that we've seen so far from the large classical cluster machines with classical CPUs, we are very optimistic that also a CUDA implementation will provide a significant amount of CPU power and a significant amount of parallelism that's on there. So the code's already structured and we will start work on this very soon. So thank you very much for watching this presentation, and if you have any questions, please feel free to write me an email. And at this point, we would like to thank the Center for Scientific Computing at Warwick University for helping us with the large runs on Minerva. We also like to thank EPSRC, who is funding Hector, the large machine at the University of Edinburgh, which we've used for our scalability studies. Thank you for your attention. Goodbye.